So welcome to video 2 on read mapping theory in this course G03 on read mapping. So what we're going to talk about here is this process where we think about these green and blue and red reads that are mapping to this segment here where A, B, and C may have repeats inside there, which complicates this process because we can see that this read that is green here goes from B to A. However, these reads in blue here bridge this area going from A back into A. The red reads are more simple because we know that A goes into C. And what we're trying to do is work out how best to deal with this this repeated mapping of this A region, which may be not fully properly assembled in our reference genome either. So when we think about these sequence reads, we have to bear in mind how they're shaped. So you may have a sequence read that contains barcodes and adapters at either end, and may have short reads that contain at the sequence portion at one end of the whole DNA fragment. If we have paired end reads, we may have knowledge about both the 5' and the 3' ends, with some sort of insert size distance between them, and maybe of the order of 300 bases, depending on the library setup. What we know in terms of our application of this is that the forward and reverse reads that containing known sequence here at either end are shared together in two separate FASTQ files nearly always, where the forward read has an ID that denotes its partner here. So it's denoted that it is paired and has an ID that is shared with its reverse read here. And therefore, when we're dealing with paired end reads, we have two read libraries that we use together. Sometimes there are interleaved reads, but they're quite uncommon. There are other types of read libraries that we mentioned before. The major two that we're going to look at are paired end reads, single end reads, and then also long reads. Less commonly, there are such read libraries called mate-pair ones, which essentially have a very, very large insert size compared to paired end libraries, but are notionally the same, but will have fewer reads because the process of making a mate-pair library is more complex. When we look at short and long reads, as mentioned previously in other courses, we have Illumina reads, which are short, numerous, and tend to be very accurate. They often have more PCR associated with them compared to the longer nanopore reads or longer PacBio reads, and they're useful for resolving each individual nucleotide. So you kind of summarize those features. They're short, high quality, typically paired. There may be PCR artifacts and very, very many. Nanopore reads are longer. The quality is becoming gradually better over time. They're single-ended, but that doesn't matter because they tend to be long. There's fewer of them because the preparation protocol is more tricky, and they may have less PCR, or indeed for many viral species samples may be amplicon sequenced. They're very good at the structural resolution of this whole area. So that's how they can be used. So we also mentioned how read libraries are also all different, that they may have different lengths depending on the read library type, and if they're paired end reads, may have different insert sizes, and then there'll be different numbers of reads there. And these are three different read libraries of all of our samples. So you can see that they're all quite different, even if they're notionally sequencing the same thing. So if we look at those insert sizes, you'll see they're quite wide, different ranges here. So to bear that in mind when we're mapping reads, paired end reads to a reference genome, that there'll be a insert size with a mean and standard deviation that corresponds to your library, and that will reflect the resolution, say, of indels that are longer than this total fragment size, including each read, and the insert size may be harder to resolve. So you can think of this process that we have this big green reference genome sequence, and we're mapping lots of different reads to that reference and trying to work out instances where maybe you have a base difference across the sites here, or maybe there's some sort of structural change at a certain segment here that will cause changes like reads to pile up at either end, but to have no reads inside that. We can quantify this coverage as the number of bases aligned to each individual base. So we can estimate what we expect from that based on the genome length, the number of reads, where we have the coverage as the length of the genome by the number of reads, the length of the read by the number of reads divided by the genome length. But this is an expected value, and therefore the value for each individual base will vary. If we're thinking about having different reads, so let's say we start with these short reads here, they may struggle to resolve certain repeats if the repeat size is longer than the total read length. So if these shorter gold reads, they're going to have issues trying to resolve this repeat compared to its one over here. Long reads that span the whole length will help them resolve that. So if we resolved this this whole region using the short reads only, we'd work out with two contexts shown here in green and green. Well, if we added a long read into that, or a long read library into that, that may in fact resolve the whole region by identifying where this repeat is for that particular region, and therefore we may get one single context. And that would help resolve this well. If we looked at another example of this, we might find that if the long read does not properly span this whole length, that still doesn't actually resolve it. So we'd still get two contexts from the short reads, and we might get one additional one from the long reads that spans part of that region. We may not get the whole resolution if this doesn't span this whole region. And that applies to any kind of repetitive region or indel or structural variant of interest. If we have paired end reads, the same applies, that if the paired end reads span this change of whatever type, we can use those paired end reads to at least bridge that to a single context where we have some sort of idea of the gap here, even if we don't know the actual sequence itself. And we can estimate that gap size based on the information in these paired end reads from the insert sizes. So we can estimate that gap, and maybe that gap is some sort of real change compared to the reference genome. So the example of it here, we may have instances where we have an A in the genome and a C in our different reads down here. And then if we look at instances where we may have a difference where there's something in the reference genome that's absent in our sample, we'll find that there's reads piled on either side. And often they'll be actually had higher coverage there, depending. We'll find that there's no reads inside this read. So when we're thinking about this whole process of read mapping, we also have to bear in mind that we're actually aligning the individual bases themselves. So if we zoom in here to these three reads here, and this is taken from this website here, we can look at actual sequences here. So we're aligning this one, TAAGCGA, to this reference sequence above. And we're comparing the number of mismatches and gaps that are present to compute a score for the mapping probability of this read compared to this particular location. And because there are many different locations across the genome, we actually have to compute alignment scores for many different locations. So the example of another read mapping here, because it has a matching CCGATA part here, and then another read here where there are some instances of a possible change. And therefore we're computing the alignment scores for each of these reads compared to the different locations that are present. Sequence alignment scores, obviously, there's different ways of computing them. So we want to get a score, we have to bear in mind what type of score are we getting by comparing the number of matches, mismatches, gaps, and we can have variations on that, like gap opening and closing penalties too. And our issue is that some of our reads may map to multiple locations, and that's often because there are regions of many of our genomes that are repetitive, and therefore that makes things more complicated. So if we think about an example here where we have two sequences, here is the reference sequence, and we're trying to align to this reference sequence of GG, CT, GG, we can use these scores, like the example on our left here, to add a positive score for a match, a negative score for a mismatch, and a gap, and then include gap opening and extension penalties as well. So these are just example values to consider this. So if we have a GG match, that might give us a score of +10. A GA mismatch might be -5. A C with a deletion or an absence of a base down here, that might be -5. A gap extension is -1. And then we have two GGs at the end. So our overall score is computed from the set of all of these. So we get 19 overall for this particular alignment. If we rearrange these bases, for this particular alignment, we won't get a lower score. More advanced methods consider substitution table and the transition transversion rates as well, that the probability of, say, going from A to a C is not the probability as the, say, from going from an A to a G, because an A to a G is a transition, whereas A to C is a transversion. So you have to consider the chemical setup, molecular setup of each nucleotide. If we look at an alignment like this, we can see that these 5' and 3' segments align very well, whereas this part in the middle is more difficult to align. Though we can see there's some mismatches, but it's not very good. If we consider how different tools that we use address this, we'll find that there are some differences, especially for problematic regions, that we might get some initial estimated alignment by looking at the CC and TT similarity as being a good option, but we still have these instances of a change here as well. And if we look further afield at other alignment tools, we'll find that actually you can come up with different alignment approaches for these regions, depending on our different approaches. So which is the best is a complex one. It depends on the scoring criteria. If we look at Novo line, SMALT, or BWA, each of these would come up with different solutions to this same alignment. And which is better is a complex question. What we can do is quantify the number of indels and SNPs for each of these changes, and that gives us a better sense. So if we do that with these lines, we see Novo line has an insertion, a deletion of 2 bases, and a substitution of G8 for CT. And then we SMALT as a deletion, substitution of AGTC here, and then GACT as well. And the BWA has a SNP, a deletion, another SNP, and another substitution as well. So which is best is not necessarily very clear. If you want to try this further, you can look at this tool on the Illinois sequence alignment website page, where you can reshuffle these sequences and compare your reference sequence against your sample here of interest, and move these bases around to try to compute the best possible score given the two. And you find that sometimes it's more tricky to do so. If we think further about the theory about how this works, there's also a major importance in terms of computational efficiency in trying to work this out. So read mapping algorithms can do fast, efficient, low quality alignments, and find that's very, very effective because of this issue of the diverse array of alignment locations in the reference genome. So for large genomes, this is actually a very key point. So you may have a reference genome here that is indexed and therefore has different seeds shown by different colors here across the reference genome. So when we're thinking about this, how these algorithms work, each seeds and all its mapping locations are stored in a reference data structure known as a suffix tree or hash table, depending on the tool. So these are two slightly different approaches that have a lot of similarity. So for a suffix tree over here, we'll record the characters, and that chain of characters becomes a seed of a particular length. And then those locations will be recorded here. For a hash table, the seeds are essentially a k-mer of length k, depending on how you want to set things up, and the locations will be associated with that. So those are slightly different structures, hash tables and suffix trees. If we think about the next step, what we'll do is extract seeds or k-mers from each of the different reads, and the relative frequency of those different seeds or k-mers in the reference will be extracted from that index that we have created already, and then we'll try to compute the different options for a particular k-mer or seed mapping to a particular location in the reference genome. You might find that there's certain locations that map well, like locations 9 and 16 here, and be able to work things out further if they are a good match. So these seeds or k-mers are linked together to form a longer chain of them, and the mismatches between gaps are examined. So these intervening regions here. So To speed things up, there's a pre-alignment stage to determine whether it's actually worth computing a proper dynamic programming calculations by looking at all the different sequence options across a sequence alignment. So that kind of looks like the table on the next page, where I compute the scores for each sequence alignment, say comparing C to C here, C to G, and so on to work out the best possible alignment of these two segments of DNA. If the preliminary estimate of the alignment score looks high, then the dynamic programming algorithm will optimize that alignment, and that will create a location in the sampler BAM file depending on the quality of the mapping. So the next stage then is to determine the most likely match for each of these high quality alignments. So if we consider our reference genome here in blue here, and we have two different locations to which our read might map. So if we think about the first location, maybe there's a single base change here shown in from T to A, but the other parts are identical. And then you might have another locations here where actually there's quite a few changes. If we look through the sequence carefully, there's more differences. So there's two stages really to read mapping. Essentially, first stage is to get the alignment scores for each of the reads that have a high quality map, high quality score compared to particular regions. And then mapping is the comparison of the best versus the second best scores. That's essentially what it boils down to, the probability of mapping at location 1 versus the probability of mapping location 2, scaled by different factors. So therefore, if a read has high similarity to multiple locations in the reference genome, that means that the mapping quality will actually be low, even if those alignment scores are very, very good. So what we're doing here is getting a comparison of different scores for different locations for two different reads where the base differences are shown in black here. And you can see that this one is high quality, there's no changes here. And this one on our right actually has a total of, how many mismatches does it have? It is quite a few, 13. And in simple terms, our mapping quality is comparable to the length of the read by some sort of scalar by the difference in these scores between the best and second best. This approximation kind of gives you an idea of how these work. So if you had a read map length of 300, because that length determines the number of potential mismatches that might be present across the whole read. And we have some scalar of 0.05, and the score between read 1 here, the best, is 100, and read 2 is 90. We might want to therefore extract reads that have a mapping quality Q greater than a particular threshold. And often these scores are capped so that you can't actually go above 60. In more detailed terms, this is from the Lee et al. Paper. We have some reference genome X that contains a region U. So there'll be many U's in here. We're just looking at one of them. And we have some read sequence that contains DNA letter. We're essentially comparing Z versus U. We may have sequencing errors, but we're assuming that they're random and not related to each other. So what we're computing is the probability of some read mapping at the region U given X. We call that Q. And that what this paper outlines is how we can estimate that based on the product of the error chances of all the mismatch bases between Z and U. So if we think about what we're calculating here is that we're ignoring the matching bases. And remember that the error probability is for scores where this mismatches is scaled by -10 by log base 10. So that means we have to use 10 to the power when computing these error probabilities. So if we have base qualities of 29 and 18, we can actually put them to the power. So we say 10 to the minus 29 for one of them. And then the other error probability is 10 to the power of 18. We'll put a minus in front because that's negative. And we can actually put these together. Bearing in mind we have to divide this by 10 for each of them. So think of that error probability as simply as being 10 by the sum of the mismatched bases up here, minus 29 plus 18 all over 10. So if we have many bases, we'd add them all in there. Here we find that this value is actually quite small. So that's the probability of Z being at U, which is quite low here. If we look at a further example, again with the same principle, probability of Z being at U given X, if we have 3 mismatched bases, if the same approaches work, when we add these all up, we find that the probability will be quite small here because you have these mismatched bases. So these indicate that these are high quality differences between the read and the reference, suggesting that the read does not actually map here. If we had low quality mismatches, so 10 to the minus 11 and 12 and 10, like the below example, you can see that you still get a lower score, but it's not as low as 1. And this might be because these mismatches might be mistakes. So what we do is work this out for all possible locations. And what we do for each location that's primarily of interest, that has the highest quality match, like U1, for U1, we work out that probability compared to the sum of all the other probabilities. So it's essentially a Bayesian approach. We get the posterior probability of U, 1 being the pace at which Z is mapping, given X. We're working out all these different options across the different reads. So you've got the sum of all the probabilities down here and the individual probability here. So the mapping probability is then computed as the Q for U1 given X and Z, scaled by minus 10 by 10 to the log 10, 1 minus posterior probability above. So we're bringing this chance down here. And that gives us a score. And we're typically interested in mapping quality scores that are greater than 30. In practice, though, it's important to note that this theory is computationally challenging for computers to implement in an efficient manner. So mapping qualities are actually estimated. So there's actually a numerical approximation to estimate these in practice. And you see more details in this paper. What this approximation says simply is that we look at the best hit, as I mentioned before, and then the second best hit. And then there's a number of other factors to take into account. So we assume, given a 28 base pair reads, the minimum number of mismatches that are possible in that seed, the minimum base quality in that 28 pair reads, the number of hits with the same number as mismatches as the second best hit, and then finally the probability of a perfect hit and a K mismatch hit in that 28 base pair sequence. So that's essentially what we're looking at here. So it's the difference between the second best and best minus a series of other parameters depending on this 28 base pair seed. So that's why the calculation is a little bit complex, but it's an approximation to achieve this computationally efficient outcome. And it's known that being computationally efficient and performing multiple rapid mapping of different reads to different locations is better than trying to have a perfect match, an exhaustive match for each individual read. In practice, if the mapping quality is, if the base quality of the read is good, so the read is good, but it has a low mapping quality, most tools will map the read to one of those locations. So in practice, that won't matter too much, because if we have 2 different locations that are high quality matches, and maybe they're repeats because they're very, very similar, if the reads map to both locations, we'll find that actually it doesn't matter because we have many, many reads. So it only makes a difference if we have very low quality coverage, then it might matter more. So we would hope that that doesn't make an overall difference too much. But what is worth noting is that the alignment scores still matter a lot, especially when you're dealing with viral haplotypes. So if we have erroneous alignments to an influenza A PacBio data, and we're trying to work out the true viral haplotypes, and as you know, viral mutation rates can be high depending on the specimen. And we're interested in this issue of we're looking at false positive SNPs. If we look at A and B here, we're looking at BWA scoring, and that gives us two different best scoring alignments, only one of which is correct. So if we see here, we have our reference genome here, TTGG. Two haplotype here is TCGG. Our read has TCG and TCG for each of these possible alignments. This one is more accurate because it's what's the mismatch versus G. However, we may find that we get a score with a mismatch at CG and a deletion at T here instead. That would be incorrect. And the same here on the right, we have CGAGG. And if we have our read here, it is CAAG. We may have one instance where there's a SNP here and a indel here, and another instance where we have an indel here and then a SNP here. Each of these are equally scoring alignments, but this one is more accurate. And there's other examples here when we consider longer bases on multiple sites. So we might have a true haplotype up here. I've mapped this read down here. We might make an insertion here compared to the reference, or we might make an insertion here compared to the reference, where we have a base difference here for T versus G, and another difference down here as well. And this matching this deletion here. Vice versa, there's another example down here where we have this read here. And if we look at the difference here, we have an indel versus the reference genome and insertion here. The other one has the same match here, but it's the T a SNP here. So this accuracy in terms of resolving the true haplotype can be an issue for certain alignment tools, and that's why we should just consider what's the best tool for our task, and that's something that is not necessarily something easy to answer, but we'll look at that during the practical itself. So please see the next video on linking read mapping with genome assembly.